What if Google just built an AI that can outperform top researchers, code entire ML pipelines, and map the Earth, all on its own? No hype, no warning, just results. These new systems aren't upgrades. They're signals that AI is about to leap past human capability in ways we've never seen before. In just a few days, Google has unveiled 3 major breakthroughs in AI, each aimed at a different domain, yet all pointing toward a shared ambition: building systems that rival or surpass human expertise in high-level tasks. From automated deep research to autonomous machine learning pipelines, and even a planet-scale geospatial AI, Google is quietly reshaping what AI is capable of. Don't forget to like and subscribe to NextCore AI. Let's explore these 3 systems and what they signal about the future of artificial intelligence. You're watching NextCore AI, where we break down the most powerful breakthroughs in artificial intelligence before they hit mainstream. Subscribe if you want cinematic, expert analysis of the tech that will shape your future. Because here, we don't just cover AI, we decode it. Segment 1, TTDR, Test Time Diffusion Deep Researcher. The first system, known as TTDR or Test Time Diffusion Deep Researcher, represents a substantial leap in AI research capabilities. Unlike current agents that piece together summaries or cite scattered sources, TTDR replicates how a human researcher actually works. It plans, searches, drafts, revises, evaluates, and repeats, refining its output at every stage. TTDR treats the research process as a diffusion system, where an initial unpolished draft evolves over time. Google tested TTDR on complex research tasks that require multi-step reasoning and deep external search. The results were striking. In head-to-head tests, TTDR outperformed OpenAI's deep research agent in nearly 3/4 of long-form tasks. Even in short-form queries, it showed up to 8% improvement on average. It was also consistently rated higher in helpfulness and comprehensiveness. Its architecture operates in 3 primary stages: planning, identifying goals and initial sources; iterative search, pulling, ranking, and validating data; final report writing, synthesizing everything into a polished narrative. Each phase is backed by agents capable of self-evolution, a method where components learn from their previous errors and reconfigure autonomously for better performance. The result is a system that maintains focus across long reasoning chains, handles ambiguity more effectively, and reduces factual or logical missteps. And because TTDR learns from its own errors, it improves with each iteration. This kind of self-improvement isn't just efficiency. It's a blueprint for AGI research agents that don't need hand-holding. It's the kind of shift that could soon replace not just interns, but full research departments. Segment 2, MLE-Star, AI for Machine Learning Pipelines. The second release, MLE-Star, is an autonomous AI agent designed to handle end-to-end machine learning tasks, from problem definition to executable code. At first glance, it resembles other AI coding assistants, but MLE-Star is much more than code generation. It builds full pipelines, optimizes model architecture, and performs component-level diagnostics, all autonomously. Here's how it works. It begins by scanning recent literature and repositories for the most relevant models, not defaulting to outdated standards. Based on data type and task, classification, regression, etc., it selects state-of-the-art models like Vision Transformers or EfficientNet, rather than relying on legacy solutions. What makes MLE-Star especially powerful is its adaptive refinement loop. It then focuses on that component, whether it's feature engineering, model ensembling, or loss functions, and runs target experiments, refining based on prior outcomes. Even its ensembling strategy is dynamic, rather than static voting. It generates custom ensemble logic, evaluates performance, and adjusts accordingly. To prevent common issues seen in AI-generated code, Google integrated 3 critical safeguards: a debugging agent to catch execution errors, a data leakage checker to prevent test/train contamination, a data usage verifier to ensure all provided inputs are properly utilized, including structured and unstructured formats like JSON, satellite imagery, or tabular data. In evaluations using Kaggle-style competitions from MLE Benchlight, MLE-Star, won medals in nearly 2/3 of all challenges, with over 1/3 being gold, significantly outperformed the previous best baseline, which only medaled about 1/4 of the time. Perhaps most impressively, MLE-Star proved adept at correcting its own hallucinations, such as improperly normalizing test data or ignoring edge case files. It adapted on the fly and incorporated user guidance when provided. All of this is available open source through the Google Agent Development Kit, allowing practitioners to begin using it immediately. This open source release also hints at a broader democratization of AI tooling. With systems like MLE-Star, small teams could deploy state-of-the-art solutions without deep ML expertise, and signals Google's intent to dominate the AI infrastructure layer across both cloud and local deployment. In Segment 3, AF Alpha Earth Foundations. The third innovation comes from DeepMind, Alpha Earth Foundations AF, a geospatial foundation model designed to interpret, compress, and generate planetary scale data. For decades, Earth observation has struggled with one persistent challenge: too much raw data, too little labeled information. Satellites can capture floods, deforestation, urban sprawl, but without accurate annotations, the data is often difficult to act on. From satellites, drones, radar, field sensors, and even text sources, into a unified, high-resolution representation of the planet. Here's what it does. It generates global geospatial embedding fields, each one representing a 10 by 10 meter tile, going back to 2017. These are compressed into 64-byte vectors, making them 16 times more compact than previous models, without sacrificing accuracy. Using learned correlations across time and modality, AEF can generate coherent maps even when data is missing, such as cloud-covered regions or sensor gaps. The architecture, called space-time precision, processes input across space, capturing local and regional spatial detail; time, modeling temporal sequences across years; resolution, dynamically adapting from coarse to fine detail. It also integrates geotag text from sources like Wikipedia, linking raw data with semantic labels. For example, connecting visual changes in land use with written descriptions of human activity. AEF is already being used by the United Nations for climate monitoring, Brazil's map biomas for tracking deforestation, and global research institutions studying long-term environmental change. One key feature: AEF can generate maps for any time, not just when a satellite pass occurred. Organizations can now access these embedding layers directly in Google Earth Engine, reducing the barrier to entry for mapping and monitoring Earth at scale. But beyond climate, AEF opens doors for agriculture, disaster response, urban planning, even geopolitical strategy. The ability to analyze and simulate Earth at this scale transforms how nations and organizations make decisions. And with DeepMind pushing toward real-time digital twins, we're entering a world where the Earth itself becomes a live data stream, a strategic asset mapped by AI. DeepMind's future plans include increasing resolution, integrating more local knowledge and citizen data, and eventually building real-time digital twins of Earth, living, updating models of our planet. Each of these systems, TTDDR, MLE-Star, and Alpha Earth Foundations, reflects a broader shift. AI is no longer just assisting humans. It's beginning to replace human workflows in domains that once required expert reasoning, coding intuition, or massive institutional infrastructure. Whether this is progress or something more concerned depends on how and by whom these systems are used. What do you think is the most transformative or potentially dangerous application of this technology? Each of these AI systems isn't just smart, they're self-evolving, and together, they show a future where the biggest breakthroughs won't come from people, they'll come from the AI we've taught to build itself. So, what part of this future excites you most or worries you most? Tell us in the comments. And if you want to stay ahead of what AI is really doing, subscribe to NextCore AI and turn on notifications, because this is just the beginning.